All right. Welcome back, everyone. Hope you had a good week. Okay, so some quick announcements. The Getty Social, that is this Saturday. Um, Unfortunately, I cannot be there because I will be in Boston, but the rest of you should come. Um, Not too late to RSVP. Um, and then also the CS Spring Town Hall is happening in a few weeks, I guess. So just like put it on your calendar, forget about it, and then day of you can be like, oh, this exists. But they do have this feedback form that they always send out. You've probably done it before. So yeah, go fill it out if you want to get your feedback heard. Ask for more cybersecurity classes or maybe better ones. So yeah. And then yeah, not too much else. As usual, we have Cyber Lab and Cyber Academy next week. Some cool talks planned, and then basketball on Friday. All right. And yeah, you've all probably done this already. So okay. Yeah, without further ado, I'll pass it off to TS for his talk on shadow stacks.
Okay, hi everyone. So today I'll be talking about shadow stacks. But shadow stacks kind of like occur as a mitigation, like to some kind of binary exploitation attack. So I'll first talk a little bit about like what is binary exploitation, and from there we'll get into like what shadow stacks are. So first start, what is binary exploitation? Okay, so binary exploitation is kind of like the exploitation of low-level vulnerabilities, which usually is like memory corruption vulnerabilities, right, in order to obtain remote code execution, right? So over here you see like a little diagram. We usually like try and look in a binary to identify like the primitives, right, which like can be like some like off by null or some kind of like small thing that you can do, right, to affect like to corrupt the memory. And using those primitives, you try and use it to like activate different functions to create like some kind of gadget. And using those gadgets, you like kind of form a tool chain that gives you like RCE. So that's binary exploitation. And so an example of binary exploitation in the wild, right, is SIG-RED. And SIG-RED leverages a buffer overflow on the heap using so this is targeting like Windows DNS servers. And so what happens is that if you have a malformed SIG query, which is a type of DNS query, right, you're actually able to like get RCE on the Windows DNS server. And so this is like was a pretty like severe thing, right? Because it gives you like RCE just by like sending a few messages in between you and the server. And it also affects all Windows servers versions from 2003 to 2019. So it was like a pretty large scale like vulnerability. So this is like the potential of like binary exploitation vulnerabilities. So yeah, as I was speaking, right, binary exploitation vulnerabilities aren't only limited to buffer overflows. They're actually like a large number of like possible like attacks as well as defenses that have been made in order to counter them. And like this is just like a little diagram to show like how far we've come. And I mean, I definitely did not make this diagram. It was like stolen, but yeah, it does show that there are a lot of things that happen. So how does the shadow stack have anything to do with this, right? So here is the time that we introduced the concept of control flow hijacking, which is a very important part of binary exploitation, right? Because there's normal control flow. So you see like block A to block B, right? And as the attacker, what we want to do is to like hijack the control flow so that it goes somewhere else, right? Like from block A to block C, right? And so this is like kind of like hacking in a sense, right? So one way to do like to perform control flow hijacking is through return-oriented programming, where we use like rob gadgets that end with a red instruction to get the process to execute what we want, right? So by training rob gadgets on the stack, right, and because a return instruction like kind of pops the stack, right, it allows us to like use to chain these rob gadgets, and because different rob gadgets can be used, right, this allows us to like kind of like program using these rob gadgets to obtain like the functionality that we want as an attacker, right? So this is just a little diagram of how rob gadgets will be put on the stack, right? So I'm not gonna go too technical about it, but basically it's just like you can put it one after another such that they trigger one after another, and in that sense you can like do what you want with it. So how can we prevent rob, right? Because like ultimately as a cybersecurity club, we are here to like prevent attacks, right? So some mitigations against rob. For under the control flow enforcement technology. Okay, these are like some very big words being thrown around, but it's basically just like a mitigation against control flow hijacking, and there are different types of methods that are shown over there. And today I'm trying to talk about shadow stacks, right? And so this is what the shadow stack solves. Okay, so the problem is that when you have a rob gadget attack, like return addresses are stored on the stack, right? But the user application might be able to like kind of like maliciously modify the stack due to memory corruption vulnerabilities, right? And so the solution, right, that shadow stacks present is that we can store our return addresses on a clone of the stack. And whenever we return, we verify the return address like every time we return. And so this prevents, right, rob gadgets from executing without like passing this check. So I just have a simple illustration of how the shadow stack works, right? So for example, okay, this is a normal like program execution. When we call the function A, what happens is that the return address from A is pushed onto both like the shadow stack as well as the stack, right? And then usually, you know, if you are a function that accepts user input, you will have like some kind of like local buffer maybe, right? That's on the stack. So for example, if you are able to perform buffer overflow, right, then what happens is that you from the buffer, right, we can overwrite the return address with certain rob gadgets as shown on the stack on the left, right? And so what happens is that because the shadow stack is like allocated at a different part of memory from the actual stack, right? So the shadow stack remains unchanged, right? And so what happens is that now when we are trying to return from function A, right, we compare the shadow stack, like what's at the top of the shadow stack with what's at the top of the current stack. And now we see that they are not the same, right? And this is the verification. So when the comparison fails, right, we abort the program, and this prevents like rob gadgets from being like actuated, right? So this is like kind of like just how the shadow stack works. So the question is, can we get around the shadow stack, right? And what do you guys think the answer is? Yeah, we can get around the shadow stack. So yes, because we can use other techniques, right, such as call-oriented programming or jump-oriented programming. So I'll just start with call-oriented programming. So the entire point of these like gadgets, rob gadgets, is to redirect control flow to where you want it to go, right? And so other methods or other like instructions of redirecting control flow include like call as well as jump, right? So for example, over here, we see the instruction, it's an indirect call. So it calls an address that's stored in a register, right? And so if we are able to control that register, like what gets put in that register, then we are able to control the control flow, right? Where it goes, where the program goes, right? And we see that if we use like this call-oriented programming, we keep on calling like new like functions, right? You keep calling, and because there's never a return instruction, right? That you will never like kind of like get the shadow stack to like activate, or like you never like result in the verification that the shadow stack does. And so like shadow stack will not mitigate your attack, right? So this is call-oriented programming, and the gadget you see it like at the top over there, it's a very good gadget, right? Because it like moves a lot of things from the stack into like RDI, RSI, and RDX, right? Which are like the first three arguments of like a syscall or function, or function. And it also moves REX from the stack. So like using this gadget is actually very strong. Like you can put all these things on the stack if you have control, and use that to like basically get like call the function that you want. Okay, the next one is jump-oriented programming. So it's kind of similar to call-oriented programming, but this time instead of call, we're using a jump, right? And then what usually happens is that you could technically have also like the other things on the stack being moved into the registers. But what usually occurs is that you have a pop and then a jump gadget, right? So over here, we see that the gadget here is popping REX, and then after that, it pops RBX, and then jumps to REX. So because we generally have control of the stack, we are able to like control both REX and RBX, and using that, we can jump to an address that we want, and we also have control of RBX to do what we want. So all these little gadgets can be chained together to kind of like perform control flow hijacking without like getting the like bypassing the mitigation of the shadow stack. Okay, so I mean this is not going to be done now, right? But I just want to say that if you want to get hands-on, like Enzo made the challenge called GAST, which like simulates a shadow stack using like some kind of like tracer and tracee. And so it requires the use of like COP or JOP in order to like read the flag. And so if you guys are interested in like trying out yourself, like try to use like these techniques, you can try it on the platform.acm.cyber. Platform.acmcyber.com, sorry. Okay, so does this mean that we are all pwned? Well, no, otherwise we at ACM Cyber will not have a job, right? So, all right, so how is like a COP or a JOP mitigated, right? In Linux, there's this thing called indirect branch targeting, right? Where every time, every like arrival site of an indirect jump or indirect call, there is an instruction called like NBR64. And this what happens is that if the indirect branch does not like land on such an instruction, right? The program will abort. I'm not sure what exactly what happened, but it will probably abort. And that's the mitigation against like this like call-oriented programming or jump-oriented programming. So another one is that for Windows, there's something called like a control flow guard. So it maintains a bitmap, which is constructed at compile time of all the indirect branches and ensures that at runtime, like the indirect branch goes to an actual function instead of in the middle of a function. So what happens is that this doesn't allow you to like jump into the middle of a function, and it kind of limits like how much functionality or how much like control flow hijacking you can do. So these are like the ways that like Windows and Linux have tried to implement mitigations without being like overly like affecting the performance. Okay, but at the same time, right, it's possible to overcome these mitigations as well if we are creative enough. So there's also there's this technique called function-oriented programming, and basically like Enzo gave me an article to read about it. But what happens is that it bypasses most of like the practical CFI implementations, where CFI is control flow integrity. And the reason why it does that is because it uses like an entire function as a gadget, right? And the reason why like using entire functions as gadgets can be good is because number one, like we are able to use like functions as intended, right? The entirety of a function. And number two, a lot of the times, like when a function executes, there are a lot of like remnant registers or remnant values in the registers that are left over. And so using these like side effects, you are actually, it is possible, or it seems possible that we can like, use like a particular like side effect from a function to like, for example, multiply the value in the register by 2 or set a value in the register to something else. So like in investigating these kind of like side effects, we can chain together like FOP gadgets to achieve what we want. So this is the idea of FOP. And then the other type of technique is to use like COPP, which is counterfeit object oriented programming. And this like uses the vtable of C++ objects in order to like chain them together to make gadgets, right? So I'll just show the example over here. Oh, okay. Yeah, so by overlapping objects in memory, right, and also overwriting like the virtual functions that their vtables point to, we can chain like different like VF gadgets together, right, in order to achieve what we want. So for example, over here you see that we are overlapping the the object that is of type exam, as well as the object that is type like simple string, right, in order to write like something into standard out. So what happens is that if you have score A, score B, and score C, and they're all added and they're put into like the score which is below, right? And if this is overlapped with the buffer of the simple string object, then if we call firstly like some addition, maybe like adding function in exam, and then we call like the like printing to standard out function in simple string, then what happens is that by chaining these together, we can print like the sum of like score A, score B, and score C to standard out. So this is how like the COPP can be used, right, in order to like chain functionality together and perform like some sort of control flow hijacking. Okay, so I concluded today without like really talking that much about what are the mitigations to these additional like techniques that I talked about. And the reason for that is because like as you see here, like there's a big trade-off between security and performance, right? If we like track every single like possible edge in the control flow graph, right, and check all of that every single time, then that will make our programs like super slow, and it's definitely not feasible, right? To make that run on binaries, right? So like what happens is that this is an open problem, right? Where we're trying to figure out like how to mitigate like this kind of control flow hijacking while also being able to produce like performant programs. And so and also the fact is that like many of these protections won't be needed if like your program does not have any security bugs, right? So basically, okay, my point is just that it's impossible to be like perfectly secure, right? There's always a trade-off between security and feasibility, and this is like the entire topic of like control flow hijacking is still an open problem that many researchers are kind of like spending time to research on. And so, you know, there's always more work to be done. And yeah, that's why I guess our club exists. Yeah. All right, thank you.
All right, thank you, TS. Does anybody have any questions for him before we move on, actually? Yeah, right off.
I was wondering, when you were talking about like call-oriented programming and jump-oriented programming, in what scenarios would that be possible? Because, I mean, like, you have to have like a jump or a call to like a register that you control, right?
Yeah.
Instead of like a hard-coded address.
Yeah.
So, in what scenarios would like that be possible, like writing code?
Oh, as in usually it will not exist directly in like the binary or like the process they are trying to attack. But usually a lot of these gadgets will exist in libc, right? So for example, like this gadget over here, like it was found like in libc, right, to solve like the Enzo's gas challenge. And like this gadget over here is very useful because like usually like your buffer, right, will be somewhere on the stack. And what this gadget does is that it moves like a lot of things from like the stack into like the important like argument register, as well as like the call function address. And so like these gadgets, like COP and JOP is like a very like possible thing. It's not like, I mean, I know when I like first saw it, I also thought like, oh, how is this possible, right? But there's actually a lot of like crazy number of gadgets in libc because libc offers a lot of functionality, right? And so like that like if you really look hard for it, there's usually some kind of gadget that can kind of like fit what you want. Not necessarily like it will definitely be there, but like there's a high like significant chance.
So do you know like how these gadgets get like created in the first place? Like how do you write code or how do you compile code to result in a gadget like that?
Okay, I'm not exactly sure like where this came about. Like I saw the function name, but I didn't really go into further. But I know that Enzo, like for his like solve script, he used set context, which kind of pulls a lot of things from the stack and puts it into the registers to set the context to like call a function, right?
Oh,
So for example, like that kind of thing, like that kind of like primitive can be used to like create a COP or GOP.
okay, that makes sense.
Oh yes, Vince.
Can you explain a little bit more about TrueOp, like the kind of for object oriented? So is the idea that you like have the ability to like allocate into like a memory region that C++ B table is that the idea? And then you just like rely on like the C++ B table to call the like existing like function if you see what
I think it's like, so you see that function-oriented programming, you're calling entire functions as gadgets. So over here, it's just that you are calling entire virtual functions as gadgets, if that makes sense. Yeah, so like you're not editing the function, but you're like calling the function in order to kind of like do what you want. So like, as I was kind of explaining over here, if you call like the exam, like maybe like calculate score function, right? Then like what will happen is that like the score A, B, C, etc. will be like added into the score area. And then if you call like the print function in like simple string maybe, then like this score will be printed to like send it out. So like it's just chaining like various virtual functions together to like, you know, do some kind of function. Oh yeah, I haven't done this in real life, so like I haven't done it myself, so I'm not like 100%.
Cool. All right, let's give another round of applause. All right, so so it's now time to split up into our groups. So we'll do the same as last week. If you remember, we'll have web up here in the front. We'll have crypto over there on the right side from your perspective, and we'll put reverse engineering binary exploitation on the left side of the room. Yeah, let's go ahead and split up.
Recording.